Associate Digital Marketer at Econ Systems, and I'll be your host for today's session. Before we begin, let me quickly walk you through a couple of important notes. You may share your Q&A panel at any time during the session. These questions will be addressed during the dedicated Q&A segment towards the end. With that, let's get started. It's my pleasure to introduce our first speaker, Aidan Browne. Aidan is a product marketing manager, depth sensing at onsemi, working within ICSD division of Intelligent Sensing Group. Over the past 15 years, he has worked across various roles, including application, product engineering, testing, and marketing, gaining extensive experience across multiple departments. Now, let me introduce our second speaker, Radhika. Radhika is a senior project lead at Econ Systems, specializing in the development of advanced 3D vision solutions for robotics and autonomous systems. She has successfully led multiple projects in this domain. With the combined experience of our both speakers, we have put together this webinar to address the 3D perception challenges in the industrial environments and key applications driving the autonomous of iToF technology. Over to you, Aidan.
Thank you so much, Indira. So I'm really excited to join this webinar today. And I would just like to start off with a quick introduction to onsemi. So those of you who may not know, onsemi is made up of two main organizations, the Intelligent Sensing Group, ISG, and the Analog and Mixed Signal Group, AMG. And within the Intelligent Sensing Group, it's split into automotive and industrial and commercial. So I'm part of the Industrial and Commercial Division, or ICSD. And the ICSD group has been a market leader in performance imaging for many, many years. And we are a market leader in, we're number one in robotics, scanning, defense, and automotive. And, we're number two, or very close to number one in security and machine vision markets as well. We have been looking at, new All right, one second. So we've also been looking at new products that we've introduced. So over the last 2 years, we've introduced up to 8 product families, 5 in 2024, 3 in 2025. We have a very resilient supply chain. We have long time available products. We're a US-based company. And we've expanded our portfolio recently to include iToF, ultra high resolution sensors, and shortwave infrared or SWIR sensors. And we continue to invest in leading edge technologies and manufacturing. And recently we've sampled our new Hyperlux products. We've acquired SWIR business, and we are continuing to expand our ecosystem. So our competitive edge lies in our application specific designs. We have an expanding ecosystem of modules and partners that we are working with, such as Econ. And we have world-class development tools to develop best-in-class imaging solutions. So those tools include, again, our modules and also our DevWare software platform, which is an industry standard now. And today we'd like to introduce Hyperlux ID, our first iToF sensor directly designed for industrial depth sensing. And it's a 1.2 megapixel resolution, 3.5 micron BSI sensor. And it's a global shutter type sensor. And it has really high quantum efficiency in the near infrared, up to 43% at 940. And it has on-chip depth calculations that enable up to 60 frames per second in full resolution and 100 frames per second in VGA. It's ideal for many different types of applications, including machine vision, factory automation, robotics, AGVs, drones, and then other consumer type applications like gesture recognition, humanoid robots. And we've designed this sensor to overcome the main challenges we see for industrial depth sensing, which include low motion artifacts. So we have a unique integration and readout structure along with that global shutter sensor and on-chip storage, high depth resolution accuracy enabled by our 1.2 megapixel global shutter and BSI pixels, low cost and small size that's enabled by our on-chip depth processing, so no extra frame memory or FPGA is required. It reduces the external compute that's required as well. We can also enable long distance with high ambient light rejection. This is enabled by our smart iToF implementation, and it allows us to range up to 20 meters further than standard iToF and still maintain outdoor operation. And we also have our standard development environment. So we continue to use the DevWare platform that we have developed for our image sensors with this new iToF sensor as well. So some of you may ask, how does indirect time of flight work? So the depth distance is calculated based on the phase difference between our outgoing illumination signal, which is a modulated light signal, and the reflected light signal detected by our sensor. And to calculate this phase, we need up to 4 different phase measurements or 4 raw frames. And we can see this illustrated on this slide here, where we have resolving the phase difference from 4 different raw frames with different phase delay between the received pixel and the illuminated modulation. And based on this, we can get the phase difference, and that gives us the distance to the object, and the depth range achievable is a function of the modulation frequency. So again, looking at the main challenges, one of the key things is dealing with motion artifacts. And if we look at standard iToF, like the image on the top left, when we throw a ball in the air, we can see that there are some missing pixels above and below that ball. And that's caused by motion blur. And that's mainly due to the readout scheme used by traditional iToF, where there's an exposure followed by a readout sequentially across the entire frame. Now, our implementation, we've engineered to reduce that motion blur by doing all the readouts together, storing that data on our on-chip memory, and then we do a sequential readout all within one depth frame. And that enables applications such as fast-moving conveyors, collision avoidance on AGVs and AMRs, and gesture recognition. Another example of how we deal with low motion artifacts or dealing with motion artifacts, rather, is here we show a video of, on the left-hand side, our Hyperlux ID sensor versus a competitor product. And we can see that we have a moving disk with objects of different heights, and we see much less motion blur. We maintain the heights of those objects on the left-hand side, where we see very high motion blur with the competitor product on the right. The other thing that's needed in industrial depth sensing, especially at shorter ranges, is really high depth resolution and accuracy. And here we're showing the benefit of having that 1.2 megapixel resolution and high quantum efficiency. And one of the things there is that we can provide simultaneous depth, confidence, and visual data per pixel. And we can see examples of this in the images here. So we can see the target objects, an image of them here. We can see the 2D mono image that you can get from the sensor. And we can also see the depth map and the point cloud. And we can see that we get, because of that 1.2 megapixel resolution, really fine, high detailed points in our point cloud. And we can pick out clear facial features and object outlines from that point cloud as well. So that enables key applications such as inspection, quality control, access and area control. Again, focusing on the high depth resolution and accuracy, what we're showing here is an object with different features ranging from 11 millimeters down to 1 and 2 millimeter. And we're showing the depth map and the 3D model here, a rotated point cloud. And we can see that we can still resolve